Hi all. Welcome to PyData Global. My name is Arliss, and I'm a developer advocate at NumFOCUS. Um, it was with my great pleasure to introduce Nathan, but I seem to have lost Nathan. So just give me a minute. He was here, and I think there he goes. You're back on stage.
Yeah, apologies. When you started the program, I got kicked
It
out.
got
So
kicked off. Okay,
yeah,
that happens. But
okay,
welcome
no problem.
back. So everyone who's joining our sessions, thank you so much for coming to this tutorial. Um, as I said, my name's Arliss, and I am the developer advocate at NumFOCUS. And it was with great pleasure that I introduced to you Nathan Colbert, who is going to give a talk or a tutorial for 90 minutes on From Features to Inference, build a core ML platform from scratch. I'm sure Nathan will dig a bit deeper into his bio, but he is an ML professional at Peacock, where he is senior management of ML architecture, focused on delivering ML across the organization. So, with that short introduction, Nathan, I'll hand it over to you to take it away.
Terrific. Thank you very much. Good morning, late morning, good evening, wherever you are in the world. Thank you for joining me today. Very excited to talk to you about machine learning platforms. It's something that I love very much and have spent a lot of time thinking about. The original title of this presentation was From Features to Inference, Build a Core ML Platform. But I ended up changing it from Inference to Features because this idea of working backwards fits very naturally into the test-driven approach we're going to use today to start with a business use case and try to motivate why we have all the components of a machine learning platform. So before we dive in all the way, let me tell you a little bit about myself. My name is Nathan Colbert. I am currently a senior manager in machine learning architecture at Peacock. I actually am trained as a musician. That's what I went to school for, jazz music. Specifically, I played the drums and ended up studying machine learning. Followed that to working at the New York Times, where I started as an analyst, launching experiments, slowly working my way onto machine learning teams, where I started taking over data pipelines and feature stores, and ultimately model pipelines, and then model deployment and delivery. And fast forward to today, where I'm very excited to be at the forefront or the beginning stages of working on a global machine learning platform that will be utilized across Peacock. So lots of cool stuff there. What does that translate to? Really just that I've had a lot of opportunities to think about this kind of problem. And I've also had a lot of opportunities to do it poorly. And so I've made a lot of mistakes along the way that have helped me learn the hard way some design patterns that I think are really valuable when considering building a machine learning platform. Okay, so what we're going to build today is a monolithic but modular, very modular, core machine learning platform. What does that mean exactly? Well, what is a machine learning platform more generally? A simple way to think about it is to start from the standard data science workflow. The goal is always to produce some form of inference, in the case of supervised learning, a prediction that we can use to, in most cases, assist in a business use case, solve a technical problem, something like that. Those predictions require features to be made. They require a model to be made. That model requires being trained. And all of these things, if you take these components and blow them out to a system that could handle this kind of thing, the components break down into those individual pieces very nicely. So the thing that makes predictions, that would be considered an inference engine. The thing that is going to have the features, the data that the model consumes to train and also to make inference later on, we typically think about storing these things in something called a feature store. Furthermore, we've got to keep these models somewhere. We need to version them. We need to make sure that they are available for both training and scoring. Typically, this is done in something called a model registry. And finally, specific to our use case today, we're going to be discussing also how to make these things communicate with one another. And we're going to do this in a way that they're completely decoupled, which we'll talk about the benefits of this over time. And because of that, we need to introduce the idea of a message bus, which is how our services are going to communicate. And if we have time, we will get into a model trainer as well. Model training is important, but I hope, even if we don't have time to get into that, some of the foundational concepts that we lay out today will enable you to take this forward, looking in that domain and trying to figure out what the next steps are. So what this talk is about specifically is building intuition for creating scalable testable platforms. This is a stark contrast for what it is not about. We're not going to talk about infrastructure as code directly, or continuous integration, or continuous delivery, or continuous deployment, or optimizing compute, or cost, or operational models. However, if you have questions about these things as we go, I'd love to talk about them. And at the end, we will have some challenge questions that focus on taking the work that we've done together today and moving it forward into a more production-ready system that deals with these kinds of challenges, because they're really just extensions of the concepts we're going to cover today. Furthermore, especially on the operational model side, I tend to think that a good software architecture enables a smooth operational model, right? We're solving a way for people to interact with the system that is broad in scope. That said, I have provided a GitHub repo for you here. It is empty. I'll put it in the chat as well. The challenge, having some Git credential challenges this morning, so we'll not be able to commit to this directly during the talk, which was my initial plan, but you are definitely able to access it. And all of the code will be available here at the end. Just a moment, let me just put this in the chat. So actually, I'll just put the end of the handle, which is this MLP from scratch. Okay, cool. Well, let's dive in. So, sorry, before we dive in, I should make a plug. If you are in Python and you're kind of new to the software architecture world, perhaps you're a data scientist or an analyst, and you're coming from a space where you mostly use Python, in pandas, for example, to do manipulations for, building machine learning models or finding or doing analytics or things like that. And you want to get more into the idea of like software architecture or like software engineering with Python more generally. I read this book a few years ago and it kind of launched everything that I do today. So I can't recommend it enough. And those who have read it, or if you go read it after this, you may find that a lot of the things that we discussed today, though not in as great of depth, match the patterns in which they're laid out here. So a really great text for you to use for further learning, if that's something that's interesting to you. Okay. This is the problem we're going to solve today. The business has come to us and says, specifically, we have a lot of different use cases around the business that would benefit from personalized predictions for users. Okay, there's not a lot of information there at first glance, but we can actually use this to get into exactly what we want to build today. I should mention as we go through here, please feel free to ask questions throughout. I will be following the chat and try to jump in as I can. And most of today, we're going to spend the time live coding. So don't think this is going to be a long deck. Just at the beginning here, we have to set the stage, right? And the stage is that our goal here is to produce predictions for users for specific use cases. We're going to start with inference, and inference is going to enable us to solve that problem very quickly. But as we expand into machine learning and talking about the requirements for machine learning models to be used for this task, hopefully we'll be able to motivate why we have to create the rest of the platform and why it is created in the way that it is. And we can talk more about that in a minute. Now, one way that you could go about this is to start from a low gear test-driven development approach, and we are definitely going to use test-driven development today. But we're not going to start at the lowest possible gear. We're actually going to lean into something called domain-driven design to help guide us in the domain model that we're going to create to represent the functions of these different services. So, for example, when we're talking about inference, or when we're looking at this right here, we will be able to start to delineate the different objects and their interactions that we want to work with. So let's talk briefly about what domain-driven design is. Now, we're not going to go super deep into this. In fact, we're going to touch only on 3 points today. But there are 3 really valuable points that I think can immediately affect the systems that you're working on. And for sure, there's a wonderful book called Domain-Driven Design that I highly recommend reading. This is also touched on the book I remember before. There's tons of great resources on this, so please don't use this as your only resource. However, the main goal of domain-driven design is to align software design with business use cases. When you look at all of the different vocabulary words that are associated with domain-driven design, they really go to serve this purpose. We're only going to cover 3 today, and those 3 are this. The first one is this idea of ubiquitous language. Really, when we define things in code, what do they say? One of the hardest things in software engineering is naming things. That's very true, right? And this kind of gives us an approach to think about that. If we're modeling a business process, the words that we use in our code should model that business process as well. And what this means is that when we're discussing how the system works, you kind of have no barrier between you and the domain experts you're working with to build out the domain. So this is the idea of ubiquitous language. Seems simple, very powerful. The next concept here is bounded contexts. Now, there are kind of variations on this theme all throughout, different approaches to software architecture. But it basically means that like the different parts of your system have very clear boundaries. One extension of this, and where the idea of context comes in, is that in the case of, when we're using this ubiquitous language to describe our processes, the same terms might have different meaning in different contexts, right? So when we're talking about inference and we're talking about a model, what do we need that model to do? We just need it to make predictions, right? At least in the case that we're doing today. Now, if we're talking about model training, what do we need to talk about? Well, we need to think about things like being able to update weights and store them somewhere. We may want to be able to do some sort of like batch training of multiple feature vectors at the same time. So those are two instances of where these are both models, but they may mean slightly different things in the context. Maybe a user ID, for example, in inference means something very specific because of the systems it's serving and means something very different in training. And so the point of this is that we can use this common language and we can build out these models logically, and then we can use those to guide our software development, which helps a little bit with some of the challenges around premature abstraction or creating the wrong abstraction, which if you've done it, is like a source of great pain. Okay, the final thing here is this idea of an aggregate. So an aggregate is really just a grouping of related objects. We're going to keep it very high level with this concept today. And the idea is what belongs together stays together. So if we revisit what we've been given by the business here, we can see we have a lot of different use cases around the business that would benefit from predictions about users. Okay, so the use cases in this situation are mapped both to the predictions and the users. So when we think about what an aggregate looks like in our system, we could think about it being like a use case. As we build this out, you're going to see that we have models that map to use cases. We have features that map to use cases. And we're going to use that as our central reference point for how we access data. Now, maybe that's not the perfect way. Maybe we'll find out that there was a better solution along the way. There's always options to refine your domain model as you go. But the way that we're going to start today is we're going to think very strongly about that. Use case, user ID, model, feature vector, like these things that are common knowledge and common language among data scientists, among the business that you're working with. And we'll use those to build out our system. Okay. All right. And now starts the fun part. We're going to try and build this from scratch. Any questions so far before I dive into coding? All right, here we go. And as you know with live demos, thank you for your patience. If you see anything that goes awry or you want to provide any feedback all along, please do so. And let's dive in. Okay, so I'm in VS Code. This is my editor of choice. There is nothing, we truly have nothing to start with. And we're going to start all the way from scratch today. We're going to go pretty quickly. But if you have questions, again, please feel free to ask. So I'm going to go ahead and open up my terminal and get our file structure set up. So first, I'm going to make a directory for our source code, and I'm going to make a directory for our tests. And then I'm going to also, we're going to use, I've been really a fan of UV lately. I don't know if you guys are familiar with this, but in case you don't have it yet, you can go ahead and install UV in your terminal. It's just a package manager at all. It's growing in scope every single day. And we can use this to get our package up and running very quickly. So the way that you do this is UV init. And I'm just going to pass in a specific Python version that I want to make sure that we use. So if we look over here in our file structure, if you're not super familiar with the terminal, what I've essentially done is just create all these files and folders from here. We do end up with an extra file here, hello.py. This is part of the UV ecosystem. We don't have any need for that, so we'll just go ahead and get rid of it. And we're pretty much ready to go. Now, there is one thing I'm going to bring in from the beginning that is not part of this. And that is a pre-commit config. And I'll talk about what this is, why we want it in just a minute. And this will be available to you on the in the GitHub as well. So the idea here is, in software development, we have inner loops and outer loops. And the inner loop is thought of as like all the work that happens in between commits. If you're not familiar with pre-commit hooks, they essentially do that. They hook into the commit process. And before you commit your code, they do a series of operations for you to check your code. Now, usually these are checks for style and syntax. Perhaps there's a linter, maybe an auto formatter. And in our case, it'll also run our tests. So this is just a way to make sure that we are running our tests frequently and that our code is being formatted and stays up to date, because we're going to do some commits today as we go. And then also, we're going to need a couple of packages, only 2. We're going to add, excuse me, let me see the server so you can see. We're going to add a PyTest, because that's the testing framework that we're going to use. And then we're going to add pre-commit, because we need it if we're going to run the pre-commit hooks. Now, pre-commit is completely optional to you. And we're going to go ahead and install those pre-commit hooks. Pre-commit install, so that we're ready to go. And here we can actually just do it from the root. Okay, and now our pre-commit hook should be good. And we can go ahead and activate our virtual environment. Now, if you weren't aware when this happened, this got created automatically by UV when we were setting up the project. Okay, I think we're pretty much ready to go at this point. Let's try and run a test and see what happens. Should say that no tests were collected. Okay, good. We're in good shape. Where do we start? This is the big question. Well, I've already told you that we're going to create an inference engine. That feels perhaps like a mammoth task. We have to make something that consumes models, consumes features, produces predictions. We want to be able to produce predictions for different model types. The scope can feel very vast. In fact, you may already be thinking of the fact that like different model architectures require different types of hardware. What are we going to do about that? And so before we boil the ocean, let's take a step back and think about, what's the simplest possible case? And in fact, what is it that an inference engine even does? Because at the end of the day, the inference engine's responsibility is not making the prediction. It's using a model to produce the prediction. Its job is also not to create and maintain the features, at least in the scope that we're going to look at today. Its job is to have access to some features that it can provide to the model. And so when you think about it that way, you see that the inference engine's job is kind of that of an orchestrator. It's going to set the stage for inference to occur, but we're going to have some things that we need to pass in there. Okay, enough talking. Let's get to making this. So I'm going to add another file here. I'm going to create a file in our source folder called Inference. And I'm going to create a file in our test folder called Inference, test inference. Okay, and now we can close the terminal, and I'm going to pull up in the first side here, test inference, and then over here on the second, I'm going to pull up inference.py. Just so you know, I'm doing like shortcuts and things like that to get around VS Code more quickly. That's how I'm pulling these things up, but just to make you aware. Okay, so where do we start? Okay, we need to make a prediction. That's our goal. What is the simplest possible way that we could do that? What is the simplest possible type of prediction? Well, it would be a constant. If we gave everybody the same prediction, that would be the easiest. So that's where we're going to start. And that's how we're going to build our test. So we're going to say def test. In fact, we'll go ahead and store this in a class. Test inference. Excuse me. And we'll say test returns expected constant value. Okay, so now the scope of our test is going to be that we want our inference engine to return a constant at first. Some questions here start, right? Well, what is even the interface that we're dealing with? We don't know. Well, we can go back to the requests that we've gotten from the business, and they've told us a couple things, right? We're going to have a user ID and a use case. So I'm actually going to create another file for this. This is a bit premature for like a typical, low gear development, but this is going to help us out in the long run. I'm going to call this file shared types. I'm going to put it in our source folder. And we're going to use this to kind of lay out some of our shared domain objects, right? And that's what we call these. So if you see here, just going to show you, for those who are less comfortable with the terminal, what the file structure looks like. Okay, and we're going to close the terminal, and sweet. Let's pull up these shared types, and let's just go ahead and establish. Now, typically in domain-driven design, you would have a proper object probably to represent something like a user or something like a use case. For us, we're just going to use simple types because we're moving quickly here, and we want to make sure that we are, conscious of the time that we have available. Sorry, open 2 windows. Let me pull this over. Okay. I'll just post this. Okay, so we're going to say that user ID is a string for our purposes, right? And what this is going to enable us to do is reference user ID throughout our code. It may seem silly to set, a type reference to just a primitive, but I think as we develop, especially in the case that we're working together, it'll help us keep track of these kind of complicated data structures that we're going to build up. And the next thing that we're going to have is a use case, right? And we're going to call that a string. And now we can return to our inference engine, and we can return to our test here, and we can say, okay, the things that we expect to have are, we're going to have a use case. So we'll call this a stub user, right? We're going to have a user, excuse me. And we're going to have a stub use case. And we're going to use this to make a prediction. Let's go and decide what our expectation is. So we're going to say our expected prediction, is we're going to set that equal to 0.5. We're going to assume just all predictions are float for today's example, right? And then we can start to think about our inference engine. Well, what's the simplest possible case? Well, we know that we're going to be getting a prediction. That's going to be our function. And we know that the business has laid out that the way they're going to get that prediction is using a use case. So here we can use our stub use case and a user. And here we'll say stub user. And now we've got to get this from somewhere, from source import inference. And we'll say inference get prediction, and we'll say this is our actual prediction. And then we can compare them that are actually are expected here. And we'll say, I have some. Okay. Now, as you may imagine, I'm not going to go this slow every time in terms of the way that we're going to test this. But if we run this test, it's going to fail. If you have any guesses as to why that's the case, please let me know in the chat. But I'll go ahead and run it. And the case is that we don't even have, well, let me actually UV run test. Sorry, give me just a minute here. Having some Python passing issues. Okay, so the whole idea is, while I'm getting this sorted out, we've laid out a test where we currently have, we haven't even attached this package to our Python path. Let me just set this up right quick. Now, typically this would have happened in the setup stage, so I did something slightly incorrect, but we'll just go ahead and do it like this for now to make sure that we have this code available to us, and we will do it as such. Okay, and now when we run our test, good. Okay, we're back in action. So the problem here is that we haven't even defined a function, so we can't test it, but this may feel a little exaggerated if you're not used to test-driven development, but this is a common practice, right, to go very, very slowly. So we're just going to solve this function really quickly by creating a function called get prediction, and that's going to take in a user, or a use case, I guess we said first, and a user, and it's going to return a float, and we're just going to return our expected prediction. We're just going to hard code it in. Having some latency on my side, okay. And then here we can actually go ahead and set some of these types too, right? This is where our shared types start to come in to be valuable. We can say this is a use case. And then here we can say that this is a user. User ID. Okay, cool. So now if we run our test, you can see we're not even using these values. But if we run them, they pass. Okay, good. We have the most basic form of inference engine. If it is the case that sorry, I noticed that there's some questions coming on the chat. If you find that this is like not very practical for most use cases, maybe that's the truth. We are building this up kind of from nothing, but we're going to start to move a little bit more quickly now. Now, I see a question coming in here. In the real world, would it help to whiteboard this out before diving into code? The answer is a mix of things. The answer is yes, probably. In most cases, that's what I like to do. It's very difficult to do in this medium, so I didn't produce that for us today. But of course, that's a great idea. The only hesitation with that is, unless you're very strict with yourself, is being careful not to come up with some premature abstractions, which is commonly happens when I do whiteboarding sessions. But yes, almost always, when you're thinking about what are the objects in your domain model that are going to be interacting with each other and how are they going to interact, making a visual representation of that is very valuable. So yeah, I apologize we don't have that available today, but we will continue to talk through it. And if you have more questions, please send them through. Okay, excellent. So let's take this to the next level. Making a prediction here is not going to work very well, but we can actually support this with testing while we stick in low gear. And we're going to say, we're going to test that we can produce a different predictions for different use cases. Okay. Now, just to save us a little bit of time here, I'm going to go ahead and copy and paste this example in because we're running up a little bit on time already. And the idea is, okay, we're going to have two different use cases, and we're going to have two different predicted values that we expect to get for them. Now, as you may be aware already, and it may feel that like we're going a little bit unnecessarily slow in terms of how we're building up this design, our existing prediction service cannot do this, right? It's only going to return a constant. But part of test-driven development is getting that red before you make it green. And we're only going to do this a few times, again, while we start in the very simple form of an inference engine. As we progress, we'll move a little bit more quickly. So if we run our test again, we have one pass and one fail. If we look at the failure, okay, here it's just saying that our stub use case is not defined. Let me just copy that down for us. And in fact, we'll just pause here because I think you get the gist, right? Where we've set it up here that we have a function that returns a constant, and we're asking for it to do two things. In this case, we're just asking for it to do one so far. So we need to expand this idea of what our inference engine is capable of doing. And this is really where it kind of starts to make sense. The inference engine is an entity as a part of our domain model that's going to have some behavior. So let's convert it into a class. And now typically, I'm going to use a data class to do this because it enables us to you just get a lot of stuff for free in terms of the way that you deal with some of the comparison that happens between classes and the way that you store attributes and things like that. So we're going to use our data class to define get prediction. Now in get prediction, we're now going to have to add self here. And we're at the point where we can start to think, we have a use case. It's going to map to different predictions. It's well agreed upon by the business and by, that we've discussed with them that those different use cases, those different predictions are going to be produced by models. And so we're at a start where we can start thinking about, well, perhaps it makes sense that our inference engine is going to use a model to make a prediction. That may have seemed obvious from the beginning, but we've kind of set it up to be the only choice that we have because we now need to make a selection based on a use case to make a prediction. So if we look here and we're going to create a new file now called models to keep track of all of our different models that we're going to produce today. And models here are going to represent just a very simple interface for what we expect that model to do. So far today, we have started building out something that we expect to make constant predictions. So to me, it makes sense that that entity that does that would be called a constant model. So I'm going to copy and paste this in to save us a little bit of time. And you'll see we have more things that we don't need yet, and we'll come back to those. I'm going to define the constant model here as an abstract base class. Typically, if you were going really slowly, you might start with a protocol. What's the difference? Well, a protocol is basically it's a typing construct that says, here's a behavior that I depend on. In our case, it's that you implement a method called predict that takes no arguments. But the abstract base class, as we move into testing it, basically enforces any subclass of this base class to implement this method to the same spec. Now, that's not it. That's a runtime check. That's not going to happen. Our code's not going to fail. It's still going to be able to run. But if we don't implement that correctly, we will be notified. So we're going to use this as an abstract base class here. And we're getting to the point where we can start to say, okay, we can use this model to make predictions. We're no longer going to make a constant prediction. But there's one more step that we've got to think about, which is, okay, we now have a notion of a model. And our inference engine needs to consume that model to make a prediction, which means it needs to get that model from somewhere. If we want to make our code easier to test, there's a few options. The most direct one, perhaps again, if we were moving a little bit more slowly, you may have considered, well, let me just inject it directly into the function signature. There are challenges with that. We're changing the interface. It's not going to be stable over time. So we've already adopted this class-like data structure, which gives us the opportunity to store this model inside an attribute. But the question becomes, how do we store it? Well, we already know this, right? We started with our domain model, which was that our use case, our aggregate, is going to be the way that we connect models to features and the way that we retrieve models and retrieve features. So we can start to think out that we're going to have inside of our inference engine, we're going to call it a model repository. And that name may sound a bit funny at first, but we'll talk about why this is going to be what we want to do. And in fact, we can go ahead and specify a shared type for this, just so that we have it available to us throughout our... Actually, you know what? We're just going to keep this as a dictionary for now, so that we don't have to deal with that. Okay, so this is a dictionary, and it's going to map, again, a use case. This is where the benefit of, that saying what this string is helps a little bit. It's going to map a use case to something. Right now it's a model, a constant model, right? That's the only thing that we have. Whoops, I'm sorry, I put this on the wrong line. Okay, so we have this model repository, and we can now use this to retrieve a model and to make a prediction. So the first thing that we're going to do is we're going to, get the model. We're going to say model equals self.model repository, and we know that it's defined by the use case, right? So we're going to put in our use case here, and then now the prediction, the onus of making the prediction is not on the actual inference engine. It is on the model. So we're just going to return model. Sorry, I got some latency here. Model.predict, and it's going to return what we expect. Now, can we modify our tests to make this run pretty easily? Yes, we can. But before we go that far, I'm going to talk a little bit about, and we're skipping ahead a little bit, what is this idea of a model repository? And why did we choose to start as a dictionary? And is that the best choice? Well, when you think about the domain of inference, its job is to pull the models from somewhere, right? And pull the features from somewhere and combine them to make a prediction. I've said this many times already, right? And however, what if that thing was the actual model registry that was being used to store and version all the models and whatever? Well, then we would have direct coupling, and we would break down the barrier of this inference engine to be able to have its own tightly bounded context, its own tight scope. So what we can think about is that, okay, we have a thing that is stored somewhere that we need to retrieve. This is like any other type of external infrastructure that we need to interact with. A common way to deal with this is to think of something called a hexagonal architecture, or ports and adapters. The idea being traditionally that you have a system that has to interact with the outside world via some infrastructure, and that infrastructure, if you're not careful, you can write your code in such a way that it depends directly on it. Say, for example, here I wrote model repository is a GCS bucket. Now, when I go to make a prediction, I need to do all of the logic that it takes to pull something out of a GCS bucket, dealing with blobs, and maybe I've got to deserialize something and like convert file types or think about file structure. That's definitely feels out of the scope of making a prediction, right? And so we can extend this idea inside of, of not depending on that infrastructure by saying that, okay, well, we should define a contract that we're both going to adhere to that enables the infrastructure to depend on us, because we're defining that contract within our domain. And what this really means is like an interface that we're going to depend on, that the external infrastructure has to implement. What does that mean exactly? Like if we make that concrete, let's use the GCS bucket as an example. Say within my inference engine, I need to be able to get a model, right? What I want to do then is define some infrastructure in GCS, no matter what has to happen for that to occur, the thing that's returned to me is going to be a model. And the interface for doing that is getting a model, and the name by which I'm looking is the use case. That maps to our domain. And so that's where, when you go into domain-driven design, they use a special word for this, which is the repository pattern. The repository pattern is essentially that. It's a layer, it's an abstraction layer for data access that enables you to extend your domain model into the way that you interact with external infrastructure. We'll drive this point home even further when we start talking about features. But before we move even further, because it's going to make our tests a little bit easier, let's just define this model repository. So to do this, we're going to take the exact same implementation that we've got here. Let's make a new file here, source/repository. Repositories. Okay, and then I'm going to close this, and then I'll open it up here. And so the whole idea is, if you look at our inference engine right now, right, we have this kind of sticky situation where we are, depending on a dictionary, which is not the worst idea, right? Like this is a very common pattern. However, like if we need to change this implementation in any way, say for example, you are in fact putting your models in a bucket, you'd have to change your whole implementation. So we're going to instead implement a method that accesses this, but the behavior internally will look very similar. So if I pull this up, I'm going to copy and paste this in to save us a little bit of time. Give me just a moment. All right. Okay, so first we start with what our contract is, right? What does it mean to interact with the model repository? Well, right now we just need it to do one thing, which is to get a model. Okay, and I'm going to copy in these imports as well so that we don't have these failures. So in order to do that, we're going to define another abstract base class. And inside here, we can encode the interface with which we want to interact with this thing that we are getting models from, right? Okay, this type does not exist yet. Let me go ahead and create it. Oops. Yeah, we're just going to create just one more entity here, which is going to be a model. And this is just for type hinting purposes to make our life a little bit easier as we work through this. Okay, and we're just going to say that it's equal to this. And so now when we go back to our repository, this models.model from source dot, okay, excuse me. Okay, import paths. Okay, so here we go. We have our shared types that we're using to interact with this use case. In fact, we can take this string and swap it to shared types.use case. And now we're all speaking the same language. So this is all well and good, but we actually do need to store the model somewhere, right, if we're going to move forward with building out this inference engine. So we need to define our first concrete implementation of this. And it's actually going to look exactly the same. We're going to make one that's in memory. So if we create an in-memory model repository, it's going to look something like this. Just a moment. Okay. Okay, let's import data classes as well. Okay, so here, and we also will need a field. And I'll talk about everything that's going on here in the code in just a moment. So what we've decided to do here, where we're going to start is a in-memory representation of what our notion of a model repository is, right? Again, we're trying to get something from somewhere. That somewhere could be in memory. But it may be the case that we need to change that in the future. Also, as you'll see in testing, this makes it easier. So what we've implemented here is actually very similar to the, oh, sorry, I commented out the wrong line here, to the behavior that we have existing right now. We're pulling this directly from a dictionary, and that dictionary is stored in memory. However, the responsibility is tightly scoped within that of the model repository. As you see here, when we're doing some sort of access, we want to think through the types of issues that could occur. Like, for example, when we try to access something in our registry that doesn't exist, we want to be able to raise an exception. Here, I've created a custom exception for that, which I will add now, and because this will benefit us later, and we'll see how that plays out. But ultimately, what we've got here is basically we've wrapped a dictionary. If you're not familiar with what a field is, in data classes, if you want to specify a default type that could be mutable, you can utilize this default factory, which is a callable with no arguments, to create this at class initialization. So that's what we're using here today. We're just going to say that this is an empty, by default, it's an empty dictionary. We have nothing in our model repository. Okay, I'm going to pause there for a second before I move on. Any questions about any of that? It's a lot of information. Terrific. Now, as this plays out, this idea of a repository, you'll realize more and more, oh, this is kind of like a CRUD application. Anytime we need to get something or add something or change something, that's kind of what these things are going to be start doing for us. And this is a good clue for you when maybe considering this is a good idea. Now, it may not be immediately obvious. You know, if you were interacting with a database, it may look more clear, like, oh, I could put a repository there, as opposed to, for example, a model storage layer. But in this case, that's exactly what we want to do. Okay, so I'm going to just create this new file, exceptions, and I'm going to create this exception for us. Okay, and these are just going to be custom exceptions that we want to raise from our domain, which enable us to make very clear error handling patterns. So I'm going to pull this up in here. Let's just see exceptions. And we'll go ahead and add in this one that we've got, which is just a very simple, model not found. Just some more general Python things. If you're not familiar, exception is always available in the namespace. If you inherit from it, you get all of the things that you would typically find in an exception that you're more comfortable or more familiar with, perhaps like a value error or something like that. So that's what we're going to do here. Now, if we go to our repository, we should be in good shape. Did I misspell anything? Oh, I just have not imported exceptions. Okay, let's move along. Let's get this thing up and running. So let's go back to our inference engine and let's go back to our test. Now, I believe we have everything that we actually need to test this and then scale it pretty quickly to supporting machine learning directly. So let's talk about that. First of all, this is no longer a dictionary, right? We're going to say that this is a repository. So we're going to pull that from our repositories. Repositories dot model repository, and we can go ahead and give this a default too. This is probably not something, probably not a best practice, but in this moment, we're going to just use it to our advantage to help us with our tests. Excuse me, let me do my imports here. Factory equals repositories. Anyway, repository. Okay, so again, this is just a we're taking advantage of the fact that this is, this class requires nothing in instantiation, and so we're just going to create an empty in-memory one if we need to. You may notice that I have some relative imports piling up here. This is just because of the auto importing and VS Code behaving in an odd way. Okay, now we can add some more behavior here, which is that instead of pulling this in this fashion, we are going to just use our new interface of getting a model, pass in the use case. The use cases we already know the name of. We know that this now returns a model. And I can close this error message. And we should be in good shape. However, if we look at our tests, it's clear that they're not going to pass. We need to make some modifications to our existing test to get it to work with this new interface. And we also need to finish setting up the first one. So I'm going to go ahead and pull that code in. And we can talk about, we can see some like concrete examples of how we implement this constant model interface and how we use the model registry to inject this into our inference engine. Okay. Just a moment, I'm going to try and kill some processes here to give us a little bit less latency. Okay, there we go, that should help. Okay, and it seems like we have some different naming conventions here. And we'll just import this from Inference, and we should be in good shape. Okay. Let's see what our hours are. Okay, so I have some red lines here, which basically means that I have some errors that are being picked up by my linters inside of VS Code. And so I'm just resolving those right now. One thing, for example, is that we are missing imports. So we're going to import our models because we need to access this constant model class. And then we need our model registry, which is in our repositories. module. Okay. Getting a lot of typhoons. Okay, here we go. Repositories. Okay. Let's see how we're looking. And this we need an import for as well. Excellent. And then inference engine. What's the issue here? Okay, we don't have features yet. So let me back up and we won't deal with that yet. Okay, we should be in good shape. Missing keyword argument for user. Okay, I guess here we've changed the name. We can go do that here because this will just continue to be an issue. User. Right. Okay, so now let's talk about what's going on in this test. Well, we've taken these abstract ideas of a model, a constant model, right? Which all we say about it is that it returns a float. That's what we know about it, and that takes no arguments. And we've taken this abstract idea of a model repository, which is something that creates a method, get model, that allows us to get a model from somewhere. We made an implementation of that, which is an in-memory model repository. And the secondary benefit of that is that we can actually use this in our tests, right? Now, typically, we would have also made a test against our in-memory model repository. Apologies for that. I can pull that up in a little bit. But at the same time, we're going to move forward with this version of the implementation. If you see, we're starting to add some structure to the complexity of, okay, we have all these different units that need to interact with one another, but in a way that allows us to control them in tiny, really bounded contexts and inject them into the different places where they're needed. So for example, here, we have our stub model repository, which is an in-memory model repository where we just said, again, we're just creating a dictionary here. And we're mapping our first use case to our first model and our second use case to our second model. And from that, we expect our first model to make this prediction and our second model to make this prediction. And now when we create our inference engine, we pass by composition that model repository. And then here, we're able to make those predictions. Now, user ID this is just probably an import problem. Let's just see what's going on here. Source. Okay, good. Yes, that's all it was, just to save. Okay, so we're going to run our tests now, as we should be doing often. And you'll see here, I typed something. Oh, here we go. I have this T to our file. Okay, let's continue. And okay, I'm just running PyTest over here. And you'll see that, okay, one passed. It's not clear which one, but it's actually the second one that we just created. Our first test is no longer passing. Why is that? Well, it's because we now need a model, right? And we now have a class, and we're not depending on either one of those things. So let's just modify our first test, update it to use the new interface, and we should be in good shape. Okay. And again, I'll talk you through what's going on here. So I brought this code in because I'm dealing with a lot of latency here. So again, we're just going to set up a non-existent user, a stub user, that's what we're going to call it. And we're going to set up a use case, our same expected prediction. Here I changed it to 0.85. We can always make it back to 0.5. So we stay with our existing plan here. We're going to make a stub model. So this is just a concrete implementation of our constant model class. And apologies, kind of dealing with computer delay. Okay, and this is going to return a constant prediction. And we are also going to, that's when we start pulling in our repositories and our inference engine. So repository. And then here we have our inference. Okay, and then we just got to pass up a couple more types. Thank you for your patience as we say where these things come from. Oh, this here we don't have yet, so we're just going to come back to this. And good. So This is just, I accidentally copied the code twice. Let me get rid of that for us. All right, okay. So now our test is actually doing the same thing that it was doing before, but we've just added a notion, a new abstraction that we're using to make those predictions, right? So in this case, we've created another constant model. It's just going to return a constant value. We're passing that constant model and mapping it to our use case. We're using this to do inference. And then in theory, we should get the prediction that we expect. So let's run our test and see if everything is looking good. Apologies, got a lot of latency coming up here. Okay, so we run our test. Good, they're both passing. Excellent. Okay, so in review, what have we done so far? We can make a constant prediction. We turn this into a more concrete or an abstract, really, concept of this idea of a model that its job is to make a prediction. But now we're moving on to the third part here, which is like our goal is not to make constant predictions for use cases. We're just building up to what the real goal is. And the real goal is that we need to make constant predictions for different users. Now, in order to do this, not constant predictions. We need to be able to make predictions for different users. And what's the simplest version of that? It's not starting right with the machine learning model, though in theory, what I'm about to describe is just a more basic case, but it's a rules-based model, right? We have this notion of a feature, some attribute about a user that we can use as a cutoff to make a decision about what treatment or prescription or perhaps prediction that we want to make about that user. And so we can use that to actually start to define the interfaces that are going to be required. So as a reminder, we have our use case up top. Our use case is mapping to some model. Our use case, as we said before, is also going to map to some features. And this is the first time we're going to see that come into practice because our models are going to need to take them in now. So here's an example of if we had started with a protocol, right? And we had said, we don't actually need this base class, this notion of a constant model. We just need this method, predict, to be implemented that we can depend on. We would actually have to be changing that interface now. Now, you could probably still take this forward in the protocol style fashion. But as we're trying to solidify, what the responsibilities of these objects are, it's good that we have this notion of a model to build on top of. So what does that mean? What are we going to do now? Well, the difference here is that we have a new model, and that model's the big difference between a rules-based model and a constant model is that all of a sudden we're going to start needing to take in features. Now, we haven't talked about what features are yet, but they are very much a part of our domain. We've talked about how they're connected to use cases. So I'm going to go ahead and create a shared type for a feature because as you'll see, without this, the data structure for this can be a little bit tricky to reason through. So we're just going to hopefully use these named types to help us get through it a little bit more. The first one we have, I'm going to just pull it out. We're working our way up to really what is a feature vector, right? So we have some number of features. Now, in the case of the way we're going to implement this today, our features are going to be a connection between a name and a value. And we're just going to say that value is some numeric at this time for our scope, which is an integer or a float. And so from that, we can get a feature vector. So this is just a single set of features for a specific, excuse me, I shouldn't use the word set because that'll confuse what we're going to say next, but it's a single vector of features for a single entity or persona or whatever. For us, we're going to take this a little bit farther. And this is kind of where that whiteboarding session comes in. We're just doing it in code. And we're going to say, okay, well, we need to connect users to their features if we're going to make predictions about them. So we can have this notion of a feature set. I'm using dictionaries for everything to kind of save us some time and keep things simple. But at the same time, we now can see that we're mapping a user ID to a vector, a feature vector. And then it's the case, well, actually, though, what we really care about is, or not, what we additionally care about is that we need to be able to map a use case to a user to a feature, right? And so that's where we get this notion of, we're going to call that feature sets. So a feature set is a user ID. Feature sets are a mapping where we connect the name of the use case to the feature set. And here, what this is going to mean is this is like our aggregate in action, right? We have a use case which we have connected back to a model. We should probably have that type in here. In the model registry, we have a use case, which is now connected back to a feature. And we're using this as kind of our central guiding principle for how we're going to access and modify data. Okay, cool. You may see where we're going with this, which is that much like model repository, now we're going to be able to support different types of models. You see, we're throwing an error here from my linter. It's already telling me that we're missing this argument features, right? That's part of just what's built in here, whatever I've got running in the background, maybe Pylance or something. Oh, Pylance. So it's clear that, like, okay, we now have multiple model types coming from inside the model repository. We need to be able to handle those. This is pretty straightforward. Now that we've got these classes to depend on, we can make a decision about what we should do based on the model type. So we can just say, for example, if is instance, apologies, getting a ton of latency when I type. Is instance. So if we say our model, for example, is a models dot, what was our new model called? Oh, we didn't make it yet, right? We stopped there. What we're going to call it is a rules-based model. Then we're going to do something, right? But we don't know what we're going to do yet. Let's go back to take a look at that model and finish working that out, because we already started talking about features and we got a bit turned around here. Okay, so let's rename this. Let's say this is going to be a rules-based model. And here, so now we have a type for a feature, right? So we're going to say shared types dot, and this is going to be a feature vector, right? Because we're going to use a feature vector to make our predictions. I'm going to go ahead and fix this. What's of import here? Okay. Excellent. So now we have two different model types, and we can use these to make two different predictions. And really, we've actually just completely set the stage for how we're going to be able to use machine learning models inside of our inference engine, right? So if we pull this back up, now we can say, okay, if we've got a rules-based model, the difference is we need to get some features, and they're coming from somewhere. We don't really know yet. And we're going to now do model.predict, and then we're going to pass in whatever those features are. Okay, and so this is the big differentiator here, right? If we have a rules-based model, how do we need to return this as well? We're going to return our prediction, right? Okay, so we're getting a little ahead of ourselves with implementing before we've kind of thought through our test structure. But again, we're guiding ourselves with this domain model that we've been speaking about at length. But we can start to think through, well, what does it even mean to get features? Fortunately for us, we have an example. We've already done this with models. Like, what's the difference for our inference engine between a feature and a model? You know, they may have a different structure and they've got to implement different things, of course. But as far as the access pattern goes, we have a thing that is stored somewhere that we need to get and bring into our current scope. And so again, what's the feature here is it's, well, not to overload the word feature, it's going to be a repository. And so let's talk a little bit about what that looks like. We're going to need a place to store our features. So we're going to build a repository for that really quickly. I'll do the whole thing at the same time, just so you can kind of see. I will bring the interface into scope as well as the implementation, so we can talk about them. So really, what do we need our repository to do right now? Well, we just need to be able to get features. So we can add that. And we know that we're going to return a feature vector. Now, the next part of that is like, well, what's our simplest way to do a repository? I've already kind of given this away earlier. It's that we always want to implement some in-memory version. Now, sometimes you may want to consider doing one that's, you know, in the file system or something like that, depending on the size of the data you're dealing with. But almost always, when you're building up a system and you want to make it testable, you know, some form of in-memory representation of your repository is going to be valuable. So in this case, you'll see we have a little bit more error handling creeping in. These are things that are going to help us out later, which I think we're going to have to rapidly go through. But the idea is, you know, if our use case isn't in there, we want to raise an exception. Once we get our feature set, if our user ID is not in the feature set, we want to raise an exception. And then we ultimately want to return the feature vector that's connected to that user ID. Again, if you look at our shared types here, you can kind of see how this breaks down, right? We're going to check the use case for a feature set. We're going to check the feature set by user for a feature vector. And then we're going to use that feature vector to make a prediction. Okay, I need to add an exception so that this will pass. And we will very, very rapidly go through why we would consider doing these custom exceptions. I think it's good to take our time with the inference engine though. Okay, so we have our repository. Now we can go back to our inference engine and implement it. And we can say, okay, now we're also going to have a feature repository. And the feature repository is just going to, in the same way that the model repository does, it's going to default to like an in-memory feature repository. So if I can get some, okay, there we go. Apologies. Okay, feature repository. And we're going to say this is a repository field. And then again, we're just going to take advantage of this default factory pattern just for the sake of making our tests a little bit easier to write as we go for now. Dot in memory. Feature. My computer is not moving quickly enough to do autocomplete. So let me just triple check the name here. Okay, here we go. Yes, we have an in-memory feature repository. And we can just make sure that I didn't misspell anything over here. I've added an extra letter somewhere. Repositories. Okay, there we go. We can do this. Excellent. Okay, so we have some features. Oh, and now we need to say where we're getting these features from. And of course, these are going to come from our feature repository. And we're going to say self.featurerepository.get features. And again, we're using that, in this case, our use case, right, to get down to that feature set level. And then we're using our user ID to get down to that feature vector level. Cool. So for the first time, our get prediction function is utilizing both the use case and the user ID, which really is the spec that we were given by the business at the start. Let's think about what this looks like in a testing environment. So now if we're going to test our inference engine, we now have a fully functioning implementation. And I will say that this is something that we can drive all the way home to making predictions for different users using machine learning models and the like. And then we're going to talk a little bit more about how to expand this out. Okay, and again, have some import errors here. I'm going to talk through this test while I'm trying to fix this as my my computer's moving very, very slowly. So the idea here is just the same as we did before, right? We want to create an environment where we can represent the behavior of our code and run a test against it. So in this case, we are making some stub users because again, now we're checking if we can make different predictions for different users. We're going to create different features for those users. In this case, I just create one feature name, but two different feature values. And so in theory now, through this process of injection, we should be able to pass in all this information and get a prediction using our inference engine that maps what we expect here. And I'm on the last one, I think. Okay, and we've got a problem with stub features, which is, oh, we just didn't attach a type to it. Let's say that this is a oops, excuse me. This is a feature vector. Oh, I haven't imported show types. Apologies. Okay, cool. Easy to fix. Okay, and let's take a look here, make sure that I think I just added a typo as well, and I sure did. Right here. Okay, so let's run our tests. And they're all three passing. So again, what's happening here? Let me make this very clear. we have established a structure, a data structure beforehand based on the domain model we've been given, which is we have a use case which maps to a user, which maps to features. And those group of features, we call that a feature vector, which is a name and a numeric value. And we've now created that data structure in our test. So here I called it stub features. And as you can see, it looks exactly like that. We've got our use case, our user, which maps to a dictionary of a feature name and a value. And now we've created a concrete implementation of our rules-based model, which here shows something very simple. Basically, if we get a very specific numeric value, we're going to return one prediction. If we get a very specific numeric value, we're going to return another. This is contrived on purpose. And then we can now inject all of these things via our repositories. So we pass our sub features into an in-memory feature repository. We pass our our model repository into the inference engine. They're both made available, and then we make a prediction. So I'm going to stop for a minute and reflect on what the scope of this actually is. Why is this so valuable? It may feel like, okay, this is a lot of extra effort. If you look at the code on the right, it's pretty short, and the task that we are accomplishing may feel pretty simple. And you look at the code on the left, it may feel complicated, but in fact, you have a lot of control over the things that you are able to inject into your tests. Now, why would we want to do this? Well, when you're thinking about what makes a machine learning platform, well, really any platform, but we're talking about a machine learning platform hard, is that it's very hard to test. It is very difficult to build up this intuition for all these different types that you have to deal with and all these different interaction points that you have to have. So if you start first by thinking of what are the patterns that I'm going to interact with this external infrastructure, and making sure that it's tightly bounded to the actual task that your particular service that you're working on is going to do, it enables you to create very simple mechanisms for running tests. I mean, these tests run in, let's see, how fast did it say? Like, what is that, 300ths of a second? And we know for a fact that our inference engine now, could we add more tests about, what if this doesn't happen, if that doesn't happen? Of course. But at the same time, the general behavior of our inference engine, we have proven out. It can take in some rules-based model that has an interface that accepts features and make a prediction. We haven't talked at all about models or about like machine learning or training or whatever. So that's really the goal here, is like the through line is how can we take a system like this and break it down into components that each have very small set of responsibilities that can collaborate in a way that is injectable, that depends on our abstractions, not some external definition, such that in this case, where we are today, we can create a simple manifestation of an inference engine where we can pass them in memory and run tests and get the whole behavior. Because the next question is like, well, actually, I store all my models at GCS, or actually all my features are in Redis or something like that. Well, that actually becomes pretty trivial, because what you need to do is not modify your inference engine or modify your tests. You know the behavior inference engine works. You can create a repository that's specific to Redis that implements this method, get features. And now when you have to test that repository, you don't have to test your whole code to make sure that, you don't have to create an instance of Redis to make sure that your code runs. You can test that, okay, when I call this thing in Redis, does it do what I expect? That's a very small surface area, right? It's tied just to that piece of infrastructure. But all of your system logic is completely independent from that. And because of that, you're able to, make that change if you need to. It's very common in my experience so far to have to deploy things across multiple clouds, for example. It may be the case that you have things in S3 and GCS and wherever else. As you start thinking in terms of these repositories, or more generally, this idea of ports and adapters, it gives you the freedom to expand over time. Okay, we have 21 minutes left, and we have not hit much content, although I think it's good. We've got very deep into this very specific representation of how you apply this. But I want to take it up a notch and talk about, okay, let's look at this at a system level. And so in order to do that, I'm going to bring in a lot of code, and we're going to review it together. Initially, I would have loved to code this for you real time, but perhaps I talk too much. And let's look at how you bring all these things together. Really, I talk about how it's tough to be able to test a machine learning platform. And that's true. It's tough in a unit in this way. But now think about the complexity of when you say okay, when I go to make an inference, if I don't have features, I need to be able to get them from somewhere. And those features, as we've already established, are not the responsibility of the inference engine, right? they're going to be the responsibility of a feature store. So I'm going to pull that in, and I'll just briefly go over it. What we're going to talk about as far as the scope of the feature store is going to be, we're just going to treat it like a simple CRUD application, basically. Because the domain of what a feature store does is, of course, pulling and modifying data, but it's far too big for the scope of what we can talk about today. In fact, it was the first major thing that I ever focused on in this space was building feature stores. So let me pull this code over so that we can have a conversation about what this looks like when you start to create multiple components to your system that you need to modify. Let me make sure my tests are still passing. And they are. Good. Okay, cool. So I can talk to you about code that works, which is always a benefit. So as you'll see here, when you look at the file structure, some things have changed. I've made some modifications. I fast forwarded into the future. And those changes are this. I've established this notion of services. We'll talk about those. Common, which is really things that are shared just across these two things. And this other entity called orchestration. And we'll come back to what that is in a moment. Let's look at what services are. Well, one of them we know very well. It's the exact inference engine that we just created, right? So this is an example of one service that we may have within our system. The other services that we may have, which we didn't have time to get to today specifically, are a feature store. In this case, the feature store is very simple. It's just an in-memory. It kind of looks very similar to what our feature repository is, but it's a separate entity. The same thing is true with our model registry. Looks very similar. And we're certainly not going to have time to get to model training, but hopefully, we'll have some time to talk about how to extend these ideas into model training. But what a byproduct of the way that we built our system is, if I tell you that we have a feature store and we have an inference engine, and the inference engine has features, but the feature store is in charge of the features, but these two things are completely decoupled from one another, they need a way to communicate. So domain-driven design gives us a lot of tools for taking these things and put them in a tight box to say, okay, this is the clear responsibility of the system, and I'm going to make contracts. Why do you make inference engine a data class? To perform the logic of inference. So in this instance, I've thought about, so data classes, yes, I use them basically for all classes at this point, just because I find them to be more readable and they've got benefits when you're comparing objects. In this case, you're kind of getting to something that is really, that we'll get to towards the end of the talk. It's like, well, does it actually even make sense for this to be the implementation that it is? And so we'll get there. So just give me just a moment to get to that. But getting back to the idea of, so we have these tightly bounded contexts where they can't communicate with one another. Now we need a way to make that communication possible. And this is where event-driven design comes in. It's really, this is probably my favorite part, so I wish we had more time to go super deep into it. But the idea is that, well, okay, we have these different systems. And right now what they do is they attempt to do their job. And if they can't do their job, they return some domain level exception. So if we look, for example, in the case of our let's see, our repositories, for example, in the feature and the inference engine. If I'm unable to access a model, I'm raising a very specific, what I'm going to call a domain level exception, model not found. This is a custom exception that I've made. It is not the job of my system to even reach out to anybody and say, hey, I need something from you. That's how deeply we've taken this. So how are we going to make them communicate? Well, this is where this orchestration layer comes in. And so what exactly do I mean by event-driven design? Well, it's this idea that things don't communicate directly, but they communicate through a series of events. And there's someone in the middle who consumes those events, or maybe a few things in the middle, and make decisions about what needs to happen next. So the business logic is decoupled from the actual service logic. So case in point, the one that we're going to look at right now in our last couple of minutes here is, let's set up the scenario that I have an inference engine. It has no features in its feature repository, and it has no model in its model repository. And I receive a request from the outside. Now, this is a bit of a ridiculous, kind of push to the limit example, right? The question is, how do we recover that state to make it that we can do, that we can complete that inference successfully? We need to go get features from the feature store, and we need to go get a model from the model registry. So what we do is we raise an exception, and we say, well, okay, here's the exception. I can't, there's model not found. And we have another entity there that we're going to call the message bus, handlers, that can consume that exception and translate it into a message, right? We're sending messages back and forth. That's what event-driven design is all about. That can be consumed by the message bus, put into some form of queue where we can decide, the priority with which we want to handle that message and let, for example, the feature store know, hey, the inference engine doesn't have features. Now, does it send the features directly to the inference engine? No, we don't even want that to happen. The feature store will publish the features. There will be an event that is emitted that says features have been published. The message bus will consume that. And we start to build up this relationship of messages and subscribers to those messages. So we have these individual services, each of which have a limited set of actions that they take. For example, our inference engine just, well, in this case, I think we've added a couple more methods, but it just, for our purposes, makes predictions. And we've added two more here, for example. We need to be able to add a model to our internal repository and add a feature set to our internal repository. And that means that the message bus can just say, hey, it's going to call the inference engine and say, I need you to add this model to your model registry, or hey, I need you to make a prediction. Let's look at this in some code and try and make it concrete in the time that we have. So I'm going to pull up this file messages. This will all be beta available to you after this call. There's three types of messages. We're going to go over these very quickly, but fortunately, they're pretty straightforward, I think, to understand. One is that we have a command. This is what you want to do. We have an event. This is what happened. And then we have an error, which is what went wrong. So if you start to think about what we've established, we have our inference engine. It's attempting to make a prediction, but it has no features, right? Or it has no model. We know that something's going to go wrong there. It's going to raise a domain level exception. Well, it needs to be somebody's job to interpret what that domain level exception is and translate that into one of these things, a command, an event, or an error. So that job belongs to a handler. We're going to stitch this all together so you can see how it works in just a moment. So for example, let's look at that exact implementation I just described. We're going to try to get a prediction. And when we try, we may get this shared exception, model not found. Now, you may be saying to yourself, well, what if this was a bunch of microservices? That doesn't make sense. Shared exception could be a perfect, you could replace this with an error code, for example, something that you've decided on in terms of, I'll get to that in just a minute, Felipe, in terms of how we're going to respond to this. And in this case, we're going to send another message. We're going to say, okay, the model was not found. Okay, so we have this message that's been sent out into the world. A message is, model not found is an event, which means, an error, which means something went wrong. And we need some way to take that error and translate it into an action. We need to translate an error or an event into an action. And an action is a command. So then we're going to have another entity that we're going to introduce here. And this entity is called, I've called it, a translator. Now, there's a lot of ways to do this. Many of them involve some sort of internal inspection of your class attributes and whatever. I wanted to avoid that today, so I just went with a pretty verbose match statement. But the idea here is that, okay, we had something happen. We want to take that thing that happened, and we want to translate that into something else we can do to help recover our system, right? This is what the message translator is going to do. And we're going to see this in action in just a moment. So here you see it consumes. It's got one, in this case, it's very simple. It's got one method, which is get next command. It takes in a message of type event or error. And we basically just hard code here. If it's a model not found, we're going to return this command, publish model for inference. And you may be ahead of me a little bit and think, oh, I think the consumer for something like that is going to be our model registry. So if we go back to our handlers and we take a look at, okay, whose job is it to publish a model for inference? It is, in fact, the model registry. So the model registry is going to get the model, and then it's going to make an event that says, hey, there's a new model ready for inference. A couple things here. One, we're not typically going to pass these things directly in memory, but for the sake of our example today. So if you see here, I truly retrieve the model from the model registry, and then I attach it to my event, and then I fire that off into the void. There's just go with me on that. This is something that you could do differently. You could put this in a third-party location. There's all kinds of different ways to handle this, but for our purposes, I think it works. And so we can follow this down and say, okay, now there's a new model for inference. That needs to be translated. What's going to happen there? Okay, so yeah, new model for inference. We need to add that model for inference. Who's subscribed to that? Well, it turns out it's the inference engine. The inference engine is going to say, oh, there's an event that says add model for inference. This event has two attributes, a use case and a model. I'm now going to add to my internal repository for that use case this model. So we're still respecting that same aggregate, that same connection between these data types. So what does this look like? Who does all this? Who orchestrates all this? Well, that power belongs to the message bus. And I'm going to skip what feels a bit like a leak code problem because we have to think about prioritization of these messages. I'll explain it, but I really want to get to this end-to-end test in the next couple of minutes. The idea is that we're going to keep track of a queue. That queue is going to have a bunch of these. It's only going to have commands in it. All of the things that we need to do in our system. While we have a remaining queue, we're going to pop a command off of that. And what we're going to do is we're going to find a handler. So just assume that we're able to find the right one. I didn't really exactly go through how that happens, but you'll see in the test. And then we're going to handle that command. This command is going to say, it's either going to tell me what happened or what went wrong. And based on that, ignore this little hack on line 28 and 29, which I'll tell you about in a minute. We're going to translate that event or that error into the next command. Now, here's where the priority comes in. It turns out if we had an error, we actually want to resolve that first. So if you look here on line 33, where it says, if our response was in fact an error, we're going to make sure that that gets put first in the queue. So we're always going to resolve all of our errors before we go back and retry our existing command. And so part of that is, that's how this whole system is going to work. Now, at the end of the day, if you were to take this all the way and you were to continue with these ideas, you'd realize, well, what about the responsibility of like returning a request to the caller and things like that? Well, we don't have time to go into like correlated IDs and like the way that you may want to handle that in a fully distributed system. But for today, we're just going to say like if we get this very specific event back, we're just going to return it, which sort of violates the interface of our message bus, but it works for our test case. Let's look at test end to end. And I'm going to take a look at what this question is. Have I heard about Fast Dream? I have not, but I'd love to check it out. I will check that out. Thanks for sharing. And again, you're getting, this is another good question because you're getting right to like, what's the meat of this challenge here? Yeah, I'm excited to answer that for you. Okay, very quickly, it seems kind of hard, right? And like arbitrarily difficult almost to test an entire machine learning platform, right? We need to be able to say, now we've got an inference engine, we've got our model registry, we've got our feature store, we've got this message bus, we've got all these events, these messages, errors, events, and commands. They're being passed through handlers, they're getting translated into other actions. But in reality, what may feel like a lot of bookkeeping has given us the power to test end-to-end that behavior of our system. If we have an inference engine that has nothing in it, can we end up making a prediction, assuming we have a model registry with a model in it and a feature store with a feature in it? So how do we set that up? It's a little bit verbose, but it builds on all the concepts that we've been talking about already. If you look here, we've got our same old stub user ID, stub use case, stub feature name, and then we've got the values that we're going to put in. Now here, I sort of had to skip over this idea of current feature vectors and historical feature vectors, but suffice it to say, if you keep following this rabbit hole down, when you build your model trainer, you'll realize, oh, wait a second, we can't train and score on the same features, so we need to have some notion of point-in-time queryability, and that's where that idea comes from, right? So that's how the feature store gets structured. But in this case, we just have an in-memory feature store, and ignore the targets example. We're just saying that this is what we have available. We have our current features. That's what we're going to use for inference. We want to get the prediction 0.42. Now we're going to create a model. In this case, we're going to use a machine learning model. We didn't get to this model type. You can see really the only difference between a machine learning model and a rules-based model from what we've dealt with today, as far as an interface perspective concerns, is like we have this other notion of updating weights. I didn't really talk about that, but I will give you the implementation of the model trainer to look at as well and to take in your own journey. But we do implement the same predict method, which takes in features, right? So it's kind of a subset of a rules-based model or a subclass. We're going to create the registry in the way that we've already learned how to do, which we have our in-memory model registry, right, that we're going to use. And now we have our inference engine. So what you'll notice, though, is our inference engine has been created without a repository for features or without a repository for models, right? And we've created our model registry and we've created our feature store, but they're not connected in any way. This goes back to what I was saying. We did a great job, making everything nice and decoupled, but unfortunately they're not communicating. And this is where the message bus comes in. So we're going to use the translator that we talked about before, which this is what consumes an event or an error and turns it back into a command. We're going to create an instance of a command handler. And all this does, this is kind of a hackish way to do this here, but is you're going to map your command to the handler that's going to basically receive it, take the command as input and do something. In this case, you have to do some dependency injection there, right? If you think about it, all of your handlers are set up to have, perhaps they interact with the inference engine for testing purposes in the same way that we've worked out so far. You want to be able to inject a very simple version of that. And so that's all that's happening here with this Lambda function, is that we're injecting the inference engine into that particular handler. We create our command, which is to get prediction, and then we create our message bus, and we dispatch that command by the message bus. And we can now check to see if our actual prediction ends up being the expected prediction. And not to bury the lead here, it does, right? And this may feel a little bit like magic at first, right? But what is actually happening is we have all this kind of like asynchronous communication happening, orchestrated by the message bus. But this enables all these services to have really tight bounded scope. And to be honest, the most fun part to me is this idea of how can we make this communication really, really strong. And we didn't have a whole lot of time to get into that. Okay, that's really the whole scope that we're going to get through today. But Felipe asked a great question, which is, with dealing with machine learning, we usually have several choices. Model configurations. In fact, I'm going to go ahead and pull up my last slide here, because I think it will answer exactly what you're asking a little bit, or not answer it, but maybe provide you with a challenge, which is that, here, if I can pull this up here, simple browser show. Okay, let's go to the very last one here. And if I can get all the way there in the next couple of minutes. Okay, our challenge questions. There's a lot of things that we left out, and one of them gets right exactly what you're talking about. We didn't talk about, for example, model training at all. We didn't talk about hyperparameter tuning. Like, is that a separate service? We didn't talk about model comparison. We didn't talk about the fact that different models require different hardware architecture in often cases, right? Deep learning models versus, maybe simple linear models or something like that. We didn't talk about that there are optimized runtimes for specific models, like TensorFlow, for example. You have TF serving that's super fast. And so I've created a set of challenge questions here, which I'll include in the repo that I'd love for you to, go consider. But what I'd say to you is that what we've done in a small way here is start to set up those same abstractions as you continue to scale out towards thinking about compute, towards thinking about something maybe even as advanced as like a service mesh, right? Which is kind of like a similar, a way to be able to, have a single entry point that manages, the interactions with these, these other services. As you start to think about containerizing these components and how they're going to communicate with one another, you can take these same ideas and apply them to that. So what I say to you is like, okay, yeah, maybe it doesn't make sense to roll our own message bus. There's Kafka, there's PubSub, there's all these solutions out there. Maybe we want to be able to use that. But maybe it's the case that we want to be able to test our system, inject a message bus that we have created so we can confirm the behavior that we expect without having to depend on that infrastructure. And that really is at the bottom. If you're going to build a machine learning platform, the thing that I suggest the most is to think about how are you going to test your system, because that is really the hardest part. And these strategies, as provided by domain-driven design and event-driven design, and written by many people, enable us to have the tools to do that. So all goes back to dependency injection, dependency inversion, ports and adapters, making these interfaces that are reliable and stable, so that you can communicate across your services. And that's all I have for today. So thank you so much. I will post the code and the challenge questions as well. And if you want to interact with me via GitHub to ask questions, if you want to contribute, if you want to work on this together, I'm available to do so. If you want to find me on LinkedIn, don't be weirded out. I just got one this morning. So please feel free to connect and reach out, and we can continue to talk about these concepts because, again, I do really love them. So thank you for your time.
Yes, thank you very much, Nathan. That was great. I think you need a drink of water. That was a lot of talking for 90 minutes there, but I'm sure everyone in this session really enjoyed it all. And you've given them lots of things to move forward with. So with that, I'll say thank you very much for presenting at PyData Global 2024. And I hope everybody who attended is enjoying the conference, and we'll see each other later in the show. So bye all. Take care.
Thank you very much.